Okay, so the perfect simulator is no longer the perfect simulator. You can see here that the set point moves all around. What it is generate a random number, and that adds or subtracts to the latitude and longitude. And yeah, so then it wiggles all over the place, just like in a real tractor. That's kind of the way mine looks like driving through that ditch on a side hill. I suppose we could simulate almost everything, including roll, and well, the dynamics of the vehicle dynamics would be hard to simulate, but this is a pretty good start. And I know all of you are going, yeah, well, a simulator is awesome, but it's not real. So how do we do it? As you can see here, the air is kind of all over the place. And this is what the steering is trying to keep up to, this air. It's great to have the I and the D terms, but man, the thing is never in the same place for more than a tenth of a second. So yeah, it's a tricky control system problem. So before we leave this, if we have this cross-track smoothing, it still has the same issues, but everything's a lot smoother. Now this is an excessive line movement, but you can see what happens when we smooth that distance off the line. Take it off less, and now it's just wiggly wild. And same with the integral term. Turn up that integral term. Again, the integral term, if we're bouncing back and forth across the line, the integral term will only mess up the actual steer angle heading. So I don't know if you can see it, but you see it count up fairly slowly. And as soon as we cross the line, it's at 3 times the rate it decreases the integral value. So if we're over here, like if we're on the left side and we're telling it to steer left, that means that we're on the negative side and we have a negative integral. We need to really cut down that integral and get back on this side of the line. So that's why going towards the line from either direction, you want kind of a slow integral. But if you're already on the other side of the line and you're pointing the wrong way, you really want to decrease that integral fast. You can't really do the normal anti-windup where you set a limit, because like in my original video there, we needed 10 degrees, to get back on the line. So it's really tricky because you don't want to limit it, but you also don't want to overshoot the line. And if you are on the other side of the line, you want to come back across that line, but you can't just outright zero it, because then you're going to cut across the line and now you have the same problem on the other side. So kind of an interesting little problem. So I don't know if this video is much helpful, but it shows a bit of some of the issues and challenges, as we oscillate back and forth trying to stay on that line if the signal is noisy. And I think that's one of the big tricks, is trying to dampen it out, but not then prevent oscillation. We can dampen everything out, but now you're just going to wiggle woggle back and forth across the line. So that's the problem. Okay, so I want to talk about this aggressiveness and overshoot reduction. They're interesting names. I didn't want to call them by their technical names. And aggressiveness is all about the distance you are from the line, and overshoot reduction, that is about the heading gain. So this one's the heading gain, and this one's the distance gain and their effect. So if we turn aggressiveness down and overshoot reduction down, what we'll do is turn auto steer off, get off the line, and then hit auto steer on. Speed up a little here. And you'll see that crosses the line, doesn't work very well. So if we turn up our aggressiveness, like how much of effect does the distance have, it works, that part works a little better. Try again. But you can still see that it crosses the line, and that's why I call this one overshoot reduction. Now remember, this one is all about the heading. So if we turn aggressiveness down, and we crank this guy up, go off the line. Now you can see that it approaches the line much more gently, because now it's trying to tell it to steer away, just like a derivative term. As we're getting closer to the line, it says, hey, slow down. But it still crosses the line. So you need that sort of distance and heading. You need the two to work together, and they generally should be pretty close. I've changed this so you can do much more heading and distance gain. So now when we take off auto steer and put it on, you can see it comes right to that line. Doesn't overshoot, that sort of thing. So that's what these two do. Now in the code, so in the code here, now we're using Stanley. The first thing we do is how far are we away from the line? And this uses the cross product form of point distance from a line. Figure out which side of the line we're on, and figure out whether or not we're going one way or the other based on the way the line was created. Extend the points of the line, and then we find our steer point, like where's our steer axle, and then find out whether or not which side of the line we're on of the steer point. And then we determine our heading. Okay, and what is the heading of the AB line, and what is the heading of our vehicle? And we subtract that, and then that becomes part of our error. So that's our heading error. And then our Stanley point is the point on the line that lines up 90 degrees from our AB line, is where's the steering point, and where is that on the AB line? And again, we make sure that our distance, the sign is correct based on the side of the line that we're on and the direction we're going. And our delta, of course, is our steering heading, our vehicle heading, minus the AB heading. And then this is part of that averaging where we just use a complementary filter and take a small chunk of the existing distance current from line and add or subtract that to our existing average. And then our distance error just becomes our distance from the line. And of course, you got to fix all the circular errors, because 0 to 360 is 1, not 360, or 360 to 0, that sort of thing. And so then we take our fixed heading delta and we multiply it by that Stanley heading error gain. And that's when we turn up this overshoot reduction, is where when we're adjusting this guy, we increase the gain of that heading delta. If this is set to 1 and we're 1 degree off, well, then that fixed heading delta just becomes 1. So as we turn this up, then the heading delta, or that error, has more and more influence. So it tries to think that, the error is greater than it is, so then don't turn to the line quite so quickly. Now, in terms of distance, here we have the Stanley gain. That's this one, the distance gain, or the aggressiveness. We're taking the arctangent of our speed and our distance away from the line. Now this creates order derivative, or what's basically the differential term, all automatically. So this is the part that makes it steer away from the line, is this arctangent term. And what a tangent curve looks like. Well, that's exactly what we're trying to do. We're trying to approach it, not go straight to the line and then try to turn. We want to turn away from the line. And so that is the tricky part, or not the tricky part. That is the important part of a path planner, be it Pure Pursuit or be it Stanley, and or the differential term, which is why we generally don't need a differential term when we're steering close to the line. We may need it close to the line, but all of this takes care of that differential term. And then, of course, we just make sure that we're not exceeding the degrees and that sort of thing. We don't, if we're limited to 40 degrees, we don't want to exceed that steer angle more than 40 degrees. There's our max steer angle. And, of course, we have to fix it if we're going forwards or if we're going backwards. And now the integral term, if our fixed heading delta is less than 5 degrees, or greater than minus 5 degrees, or less than 5 degrees, and our distance error is 30 centimeters away from the line, then we can start to add up some integral term. And so then this is a little bit sneaky. So remember I was saying about if we're already over on the other side of the line and we're steering the wrong way, well, then our integral term needs to decrease very quickly. So if we're in that condition, then decrease it at a rate of 3 times the rate that we want to increase it. Because we don't just want to steer to the line with an integral term, because then we'll just cross it. But if we build it up slowly and get to that line, then the error becomes less and less, and our distance becomes less and less, and our integral term will increase less. But the trick is, if we're sitting at, say, a 5-degree correction, just because you cross that line doesn't mean that you can reset it to 0, because now you're going to be zooming straight down that hill. And that doesn't work. But if we decrease it quickly, suppose the position changes like that noise does, decrease it fairly rapidly, but we can't lose that steering or we're going to lose our position immediately. And if it's not, so once we figured out which direction we are we on the right side of the line? Are we already oversteered? And once we fix that, or are we wanting to steer to the line, then all we do is we add that integral value to the steer angle, and that's it. And if we're out of scope, if we're not within that 5 degrees and we're not within that 30 centimeters, then we just zero out the integral, because it doesn't matter. The last thing you want to do is having the integral now fight with our steer angle that we're trying to generate based on either pure pursuit or Stanley. So these two will always be fighting against each other, because as the integral term increases, it will take away from the steering angle, but that may not necessarily be right, because now you have, say, a 2-degree integral term and a 1-degree steer angle, when you really should just have 3 degrees of steer angle. And so again, the two will be fighting. But then as you go on side hills and as you go on straight, this rapid decrease of the integral seems to make that work pretty well. So if anyone has any ideas on how to make this either simpler or more effective, I'm all ears. But this is kind of a bit of a breakthrough in terms of how this works and how effective it works. And again, I'm kind of limited to just driving on really steep side hills and with one wheel brake on, but it always pulls it right back to 0, and it doesn't overshoot. Even if you're on a side hill and you change the AB line position, it if it changes enough and you exceed this 5 degrees, it zeroes out the integral and she crawls back up to that line. And then by setting the integral on how quickly you want to react, then again, if you're having a fast increasing integral, remember at 3 times it'll also decrease it at 3 times rate. Now you could set this to 5, you could set it to 10, depending on some experimentation. Maybe this number here on how fast we decrease from oversteer could be on a slider as well. But again, just a simple number seems to work pretty well, and then there's just one less setting. So I hope some of that makes sense. Yeah, and then this is all the angle is the steer angle is what we send to the Arduino. And the Arduino's only job then is to make sure that the wheels are pointing at the steer angle we're sending it. That's it. So there's no integral term with the steering. And again, with that wiggling back and forth like this, doubtful whether a D term or an I term are even remotely required, because I don't think that that's the problem. It finds that 0 pretty quick. But that can be played with a simple small integral term within this steering on the Arduino that can be easily added. So still might play with that. Anyway, I'm sure you're confused now, and that was my goal. But that's kind of what I've been working on. Anyway, thanks.